Okay, let's look at another challenging question. So this question addresses the question as to whether you can have side-side angle information, and will it lead to a unique triangle if you have side-side angle, or does it really lead to two different triangle configurations? And so obviously I think some of you have seen this before, that actually leads to two different possible triangle configurations. Okay, so let's say you're given a 30-degree angle next to a side of 8, whatever units it is, and then that's next to a side of 5. Now the question is, this last side that's a 5, if you think about it, there's two ways that could fit. The 5 could kind of swing this way, or it could swing that way. And there's really two triangles that come out of this situation. So let's see how the law of sines kind of supports and goes along with those two situations. Okay, so what you want to go ahead and do, I'm going to cover that up for a second. Let's look at this one for a minute. So what we're going to do is have sine of 30, okay? So you always want to do that, okay, over the side opposite that. I'll call this b, okay, equals sine of b over 8, okay. So sine of 30, fortunately, that might be one of the values you have memorized in your head. That's really kind of nice for a problem like this one, that's a little bit longer. That's a half over 5 equals sine b over 8. Then I cross multiply, I'm going to get 4. 4 equals 5 sine b. So I get 4/5 equals sine b. Okay, and then of course to find the angle there, I'm going to do sine inverse of 4/5. Maybe 0.8 is easier to do on your calculator. But here's the thing, if you do that, okay, so go ahead and do that. Second sine inverse of 0.8. Because of how sine inverse works, it's only going to give you the one that falls into the range of negative pi over 2 to pi over 2, okay, or negative 90 to 90 in degrees. Okay, so it gives you b equals 53.130. Okay, so the thing that's going to be a little tricky about this is when you look at this, this triangle here, that's clearly not 53 degrees, but that one could be 53 degrees. That one's much more realistic of being 53 degrees. Okay, so you already have one of the angles, so that obviously is going to go with the larger triangle. Okay, so to get the obtuse angle, it turns out that, let me show you this on the side. Okay, so if you have an angle, let's say you have an angle x, okay, and then if you have like 180 and then you go backwards x, okay, those points are going to give you the same sine value, okay, it's going to be like the same vertical height. So it turns out that sine of an angle is the same as the sine of 180 minus that angle. And you could try that out with a couple values on your calculator. If you didn't believe me, you could try sine of 10. Is that equal to sine of 170? You should find the same values. Okay, so what that means for this problem is b could be this angle, or b could be the supplement of that angle, and they both have the same sine value. So I could do 180 and then minus 53.13. Okay, and I'm going to get 126.87. Okay, so that is going to be the other, I'll call it b sub 1 and b sub 2 maybe. Okay, so basically what's going to happen in your two triangle drawings, let's go ahead and draw them out, okay. So the one of them is going to have the 126.87, like that, okay, and you can, all the other information still stays the same. Then that's a 30-degree angle, and A is 5 for this one. Okay, and then there's also going to be the other triangle that you're going to want to work through, and that one is going to be, that angle is going to be 53.13, okay, that's still 8, that's still 5, that's still 30 degrees. So what you have is two triangles to work through at this point. So you'd want to continue working with that triangle. All you have to do is find one more thing, because you can subtract from 180, do 180 minus that angle to get that remaining angle. And then same with the other triangle. So all you have to do is find one more side for each triangle. And of course you could do that by the law of sines, by filling in, you know, once you find that angle by subtraction, that angle over that angle, say, equals that angle over, sine of that angle over that. Okay, so I hope that's clear enough. So let me just write out one of those. I could do sine of 30 again over 5, okay, right, equals, and then obviously I'm going to have to get that angle first. Let me do that real quick. So I'm going to do 180 minus 30 minus 126.87. So I subtract all those. Okay, so this one gives me 23.13. So I could do sine of 23.13, okay, and let's say I call that side C, okay, little c, equals that over c. So I would just need to solve this to find that remaining side C. And then obviously you have to do that for two triangles. So it's a little bit more involved of a problem, yet I feel it's such an illustrative problem about making connections about geometry, why side-side angle doesn't work, but how it's, you know, still consistent with all the other facts that you know. Okay, so moving onward, let's look at a couple other questions that you might see. Okay, so let's take a look at this one. Okay, so this one is just a triangle, but what you're asked to do is find the area of the triangle. Okay, so you're only given side lengths. Okay, so I told you you could use the law of cosines in working through a problem like this one. Okay, so you could find any of the angles, but I'm choosing to find angle A, but you could find whatever angle you wanted. Okay, so I'm going to use the form that's solved for cosine of A, which would be this one. And then you just want to plug in everything, which I went ahead and did for this one. Okay, and then once you do that, you're going to get cosine of A equals something. Then you're going to want to do inverse cosine to get an angle. Okay, so once you have that, that's pretty helpful. What you can do at that point, you have an angle, the 46, so I can write it in, 46.567. And you can draw a height for yourself. And of course, then you could do, well, actually, let's find the height first. Okay, so I could do sine of A is h over 2. So I'll go ahead and work that through. I went ahead and did that. So I went ahead and got 1.452 after I solved for the height. And then, of course, what you can do is, I'm going to show this all on one paper, so you're going to have to forgive me on this. 1/2 base times height, if you remember the triangle, looks like this. Okay, so again, I found the height in the other part of the problem, so I'm going to do 1/2, the base is 4, and then the height that I found was 1.452 for this problem. Okay, so crunching that out, I get 2.905. If you're interested in doing a check, you don't have to, but here's an option for it. In one of the videos, they presented a formula, and it was called Heron's formula. But if any of you are like, oh, I really, really want to get this right, you can check it this way. So the way this formula works, it looks like this. S is what's called the semi-perimeter. So what you do, you find the whole perimeter, the whole thing, and then you take half of it. Okay, so in this case, the perimeter of the whole thing is 9. And so half of 9 will be 4.5. So you plug in 4.5 for every S value, and then you just plug in A, B, and C. And then you have to, plug it into all that and take the square root. So I went ahead and worked through all of that, and as a check, lo and behold, I got the very same exact answer, 2.905 when I plugged that all the way in or whatever. So it's very, great to confirm that that's the, same area as I got the other way using trigonometry. Again, you don't have to do this, it's just a check. There's a couple other area formulas in the book for finding the area of a triangle given side. So there's some other ways to do this problem for sure. Again, this is one of those problems that there's obviously lots of different ways to do it. So, you're free to do whatever you would like to do for that problem. Okay, even if you decide not to use the law of cosines, that's totally fine. Okay, so let's look at some other problems. Let's look at a problem like, give me a second here, this one. Okay, so I have the cube root of x equals the secant of x plus 5. So this is a rather hard problem. Okay, all right. So what you might want to do first is think about the transformations on the right. So the absolute value of the secant x, what is that going to do? The absolute value of the secant x is, it's just going to kind of act like secant x, except the parts that are down below, like this, are now going to flip above. So it's going to be a bunch of U-shaped things. Now that would usually be 1 here, but after that, we're going to shift the whole graph up by 5. Woo! Okay, so let's think about what that's going to look like. Okay, so in other words, it's going to go up to 6, because like 5 would be like, you know, kind of like where the center line used to be. Okay, so that's going to be like 0, 6. Okay, and then it's going to have a whole bunch of these U-shaped things because those were all reflected up above. Okay, so that's just the right-hand side of the graph. Again, it's not drawn perfectly. Okay, the cube root of x, hopefully you know the gist of that. It's going to look kind of like this. Going to go through -1, -1, 0, 0, and 1, 1. And then the key thing here is what's going to happen here, okay? Are they going to intersect or not? Okay, so it turns out, if you think about it, the cube root of x is going to continue to grow as I put in larger and larger things for x. So if I put in like, let's just put in 1,000, the cube root of 1,000 is 10, right? So I'd have to go really, really far on the graph to see it, which is why this isn't really a great calculator problem, because you'd have to make your window really, really, really huge to see an intersection. But if you think about it, there actually is going to be an intersection. You can obviously plug in 1,000 and get 10 out. And of course, that's going to intersect through there somewhere, right? As soon as I get through 10. So the key thing on this one is seeing that this one continues to grow, albeit slowly, but it's going to grow enough that it is going to intersect this graph at some point. So that's kind of a trickier question for sure. Okay, let's go ahead and do a few more questions. Okay, so let's see if we can do this one. Okay, so we have cosine inverse of x equal to the square root of negative x. Okay, so this is great because it reviews a lot of cool things that we've learned in the course. Okay, so cosine inverse of x, if you have to look that up or whatever, that's okay. It looks something like that. And then this transformation, remember, is like a horizontal flip. So it's gonna, instead of growing like that, it's gonna, x and negative x are gonna change places with each other. It's gonna go something like that. So they're not gonna touch at all if you think about it. You know, they get a little close, but they don't touch. So those graphs are gonna be socially distanced for us. I'd actually thought about making a question where like, are the graphs 6 graph squares apart, but I decided that was a little bit too tricky. So anyway, do the graphs touch or not is basically the question you're going to ask for these graphs. Okay, so I think that's most of the questions that might have been a little bit tricky and puzzling for this set of problems. Hopefully, after some of these quick explanations and so forth, a few of the problems make a little bit more sense than they did before, and you can put things together and so forth. If not, just do your best with every single problem. Write down, you know, every formula you know, every fact you know on every problem. If you have to solve the problem in degrees, do that. Just write down everything you can possibly write down for every question. I will be very generous with the partial credit. I'm just interested in seeing what you can do and how you can apply your knowledge to some problems that are a little bit more applied, and just kind of put things together in a new sort of way, just to make sure that, you know, you have the handle on the information and you can apply it in really creative ways. All right, thank you.